In this video, we are going to start to introduce this idea of a derivative, right? And so in short, a derivative is a slope. All right, so I'm going to be using that word all the time, that if the word derivative comes up, I'm also going to be comparing it to a slope, just to keep that in the back of your mind that it's a rate of change of some kind. Okay, so with that, a rate of change in the slope of a tangent line. So if we have an average rate of change, this was from something prior, it's really the slope of the secant line, which is given by this equation. This is kind of your y2 minus y1, x2 minus x1, which is, this is our graph. So we're trying to find the slope at this point, and the best that we can do is just basically a secant line. So we're finding the slope between those 2 points. All right, and then an instantaneous rate of change would be finding the slope at that point versus the secant, which is just kind of a rough guess. So if we're going to find the slope of the tangent line, we're going to be doing the limit as x approaches a. So we're going to squeeze this, right? So we're going to bring that point closer and closer and closer, and it's going to change that slope and make it more accurate to that point. So that's what we got going on. All right, so start with a word problem. So it says a rock is launched vertically upward from the ground with an initial speed of 96 feet per second. So there's our velocity. The position of the rock in feet above the ground after t seconds is given by this function. Right, and this is our position function. So this refers to gravity. Excuse me. This refers to gravity. This is our initial velocity. And then the fact that we don't have any value at the end of it means that that's our initial height. So our initial height is 0. So just to kind of put some pieces together before we do this. So it says, consider the point 180, which basically means we're in seconds and we're in feet. So at 1 second, we are at 80 feet in the air. Okay, so I could find that out just by plugging 1 in, and it would add up to 80. So it says, find the instantaneous velocity of the rock 1 second after the launch and find the slope of the tangent line to the graph of S at P. So when you see the instantaneous velocity, we are doing this right here, right? So we're going to be doing the limit of this slope. And then when we're finding the slope of the line tangent, those things really mean the same. So we're talking about the tangent, and then eventually we're going to use that. So this instantaneous velocity is the tangent, and then we're going to find the equation of the tangent line, right? So we'll kind of put all the pieces together. So well, let's figure this out. So part A. So part A is the instantaneous velocity, which is the slope of the tangent, right? So that's going to be our limit as our time approaches 1. Okay, and so we're going to be doing, we'll do S of t minus S of 1 divided by t minus 1. All right, so at this point, we're just going to plug things in. So if we plug things in, we're going to have a bit of a problem, and we'll talk about that in a second. That let's just do some math right here. So S of t is just this equation, right? So that's going to be, we haven't done the limit. So at some point, we're going to do the limit, but we're going to sub out. So S of t equals this equation. So negative 16 t squared plus 96 t. And then minus S of 1, which is right here, right? So S of 1 is 80, so minus 80. And I like to keep things in parentheses just in case we have to do some distribution to it. All right, and then divided by t minus 1. Okay, so let's do some math here. So if we put this all together, we're looking at the limit of t minus 1, or as t approaches 1, of negative 16 t squared plus 96 t minus 8 divided by t minus 1. All right, here's where we're going to have a bit of a problem, because if we were to take this 1 and plug it in, right, here's what we're going to get. So if we take negative 16 times 1 squared. And then plus 96 times 1, and then minus 80. We'll get that on the top, and we're going to get a 0 on the bottom. So if we were to plug in right now, that's what the limit wants us to do, is we have to plug in. But we're going to get a 0 over 0, which the limit exists, which basically means that we have a hole of some kind, which also means we need to do some manipulation. All right, and that manipulation is we need to factor this, and I bet there's a t minus 1 that we can cancel out. All right, so if I factor this, so I got a little bit of side work to do. I'm going to take a negative 16 out. All right, I would have tested and see if a 16 goes into all of them. We did that, so I know that happens. So if I take a negative 16 out of all of them, I'm going to get a t squared minus 6t plus 5. All right, and that's over our separator workout here. And that's going to be over our t minus 1. This is factorable, so say negative 16. We have things that multiply to 5 add to negative 6, so t minus 5, t minus 1 over t minus 1. All right, there's the problem. If we plug 1 in, there's our 0 over 0. So now we're really doing the limit as t approaches 1. So we remove the hole, and we're really doing negative 16 t minus 5. That's what we're doing. So let's drop the limit by plugging in our value. So we're looking at a negative 16 times 1 minus 5, which is negative 16 times negative 4, which multiplies out to 64. So what does that mean? That is our slope, our instantaneous slope at 1. Right? That's what we're looking for. So let's give it value 64 feet per second at that point. That's our rate. All right, so part B. Part B is find the equation of the tangent line. So the equation of the tangent line is our tangent line is going to be a linear equation, i.e. we're looking for a y equals mx plus b kind of a thing. So the idea is visually, we have this quadratic that is a negative 16x squared plus 96. So it has this kind of a look to it, right? And then at 1 second, we're at a height of 80, and we are going at a speed of 90 or 64 feet per second. So we're creating this linear equation is that if gravity wasn't pulling us back down, where would we be going? What's kind of the trajectory that we have going on? So we are going back to kind of algebra 1-ish kind of a thing. We're going to be using this point slope is one method that you can do. Not the only method, but it is an option. So point slope form needs 2 pieces of information. Here's the formula. Equals m times x minus x1. We need a slope and we need a point. Well, we have a point and we just found our slope. So we're going to be doing y minus this y value of 80 equaling this slope of 64 and then x minus 1 for the x value that corresponds with the 80. We'll distribute y minus 80 equals 64 x minus 64, and then we'll add 80 over. Y is going to equal 64x plus 16. So what I like to do after this is I like to take this graph it in Desmos, plot this point, and then graph this line and see, does it pass through perfectly through that point, and does it look like it's tangent where it just kind of grazes through that quadratic? Everything should line up perfectly, and Desmos is one of the best ways to kind of throw that all in and make sure it works. All right, so that was kind of a brief introduction. We still haven't gotten to the derivative yet, but remember the derivative is finding a slope, and that is what we did. So this limit right here is basically where this idea of a derivative is heading towards. All right, we're going to have a couple different looks to this at some point. So we found the slope, which was our limit, our slope at the tangent, which is our limit, and then we use that slope and that point to find the tangent line. All right, and then we'll do another one in the next video.